Hi, welcome to an introduction to audio programming, a presentation of the 1X Developer Podcast. I'm Brendan,
And I'm Colin.
and this is a segment we call Make Mine a Double Precision Floating Point Value.
You
uh,
never get tired of saying that, do you?
I never, I think it just rolls off the tongue. I think it's really funny for some reason. Einstein may have said, if you can't explain it to a 6-year-old, you don't understand it yourself. Here at the podcast, we say, if you can't explain it after you've had a six pack, you don't understand it yourself. So that's what we're doing today, having a couple of
Do you
beers talking about audio interface.
do you want to share your screen?
Oh, yeah. Should I start over?
No, I think that's good. I mean, we've seen those slides before.
Yep, sorry.
A little bit of math.
A little bit of math. All right. Some of this may sound like dead simple basic if you are versed in this stuff, but again, we're going to start from the ground up and work our way up. Frequency, how quickly a sound wave is oscillating, measured in hertz. So it's how many times it's oscillating per second. Then we have this concept, this musical concept of pitch, right? This is the note that's associated with a certain frequency. So we, A4, middle A on a keyboard, oscillates at 440 hertz, right? So we've assigned these kind of names to certain frequencies, and we're not going to get too much into like music theory and stuff like
Okay.
that, but it's worth. I think one of the things that's worth knowing is that there's a mathematical relationship between different um, different notes of the same pitch class. Maybe is the same way to say it. So A, middle A at 440. If you go to the next A up, that's 880. It's doubled in frequency. And if you go to the next A up, it's doubled in frequency. It's 1760. So that's like, to me, that was a real moment that things clicked. Was like, there is a, from time immemorial, there has been a mathematical relationship between these things that we like perceive to be similar but not exactly the same, right? This is an A, this is also an A in some way, this is also an A in some way, right? And it's because the frequencies are being doubled.
Yeah, no, I'm really excited about this part because this is something that I was found really interesting. Like, I remember asking in uh, whenever learning an instrument or studying music theory, like, okay, but like, why does it work like this, right? Like, okay, yeah, the teacher will explain it in some way, right? Like, okay, there's no black key between C and D because that's the way it works. It's basically the answer. And
Yeah.
like one of the things that I always wondered is like, okay, but why does it repeat? Does it arbitrarily repeat? Well, no, it doesn't, because we know that C and E relate to each other in the same way no matter where I'm at on the keyboard, right? And the reason for that is because of this, I guess, because it's um, you've got the same amount of
It's about ratios.
ratios. Yeah, it's the same ratio between each note at each frequency.
Right. Yep. And yeah, we've it's kind of funny, but yeah, I have a lot of those same questions, but we've kind of decided in Western music that like these certain ratios sound good together. If you're, if you've done music theory, like a third and a fifth, and like
Right.
these these are when you talk about these things mathematically, these are representations of ratios. Um, and so the ratio from an A to an A is I guess 2 to 1, right? It's doubling.
It's a double. Yeah.
But the ratio from A to the C to the E, this is a ratio that we find pleasing.
Yeah.
Um, yeah, I don't know a lot around that, but I think it's worth knowing that like just that there are that's a real thing. There are The ratios between these notes are roughly equal. I think we kind of fudge it in Western music where we're like, yeah, it's
Oh,
close.
probably. Yeah. Well, and that's the really interesting thing is that, when they were making pianos and writing this stuff down and picking letters, they didn't know anything about like frequencies and like electrical frequency or how the ear even worked. They just knew like, okay, there's a pattern here. This sounds good, and this sounds, So,
It,
yeah, very interesting.
yeah, exactly. That's why I picked this octave example as like the one example to focus on. Is like from from time immemorial, people have been like, wait, this note is kind of the same as this note. Like, right? These are kind of the same thing, just in a higher register. Um, I think that's really important to kind of like wrap your head around is that these are yeah, these concepts are not this isn't even really like Western music theory. This is like a mathematical relationship.
Right.
All right, Colin, you're gonna have to help me out here. Let's talk about sine waves.
Okay. This is a unit circle.
This, yes, this is a unit circle.
Yeah.
So this is a circle with a radius of 1, right? So you got 1 0 0 1,
Yeah.
right? I think we're all familiar with this. Um, the If you're going around the circle, starting from this point from 1 0, if you're going around the circle counterclockwise, what you end up with is 0 degrees, 90 degrees, 180 degrees, 270, right?
Yep. With you.
Do you remember radians?
Yep.
Okay. So radians are a different representation of angle. Radians and degrees are they can be, you can translate between
They
radians and
correlate.
degrees.
Yeah.
Yeah. So a lot of people who know a lot about this stuff prefer to use radians. So the equivalent of 90 is, well, maybe the easier way to say it is halfway around the circle is pi radians, and so half of that is pi over 2, and then all the way around the circle is 2 pi, or
Mm-hmm.
back to 0, right?
Yep.
So what we end up with, the way that this relates to the sine function is the sine function is a function that takes in an angle and it outputs a ratio of, give me your SOHCAHTOA here. It's the opposite to the hypotenuse.
Yeah.
Okay.
Opposite of our hypotenuse.
So it takes in an angle, it outputs the ratio of the opposite, the length of the opposite side to the hypotenuse. And and so what you end up with here is that, you know, in general, people will use a computer to calculate sine function, but
Yep.
it is really helpful to know some of the important, like kind of key values of the sine function. That is, sine of 0 is 0. Sine of a, straight up, a quarter way around the circle, pi over 2, is 1. The sine function of pi halfway around the circle is 0. Sine of 3 pi over 2 is negative 1. And then and then sine of 2 pi or 0 is back to 0, right?
Yep.
So yeah, I really had to like revisit this and kind of wrap my head around it. I didn't remember any of this from high school, but like the point is, if you're moving around this circle counterclockwise and you stretch that out over time, if you do that not like in the abstract, but if you do that in real time, you end up with this waveform, right?
Mm-hmm. Because it continues. Like we end up back where we started, and then we repeat over and over again.
Yes. Yes. It goes on forever. And so yeah, that's why I'm saying sine of 2 pi or sine of 0 is always 0. So you have these values that correspond to like the peak of the wave and the trough of the wave, and then back to 0. Um, that's going to come up again a little bit later. I just wanted to kind of like mention that because that was a really that was a tough one for me. This comes up a lot. Sines and cosines come up a
Mhm.
lot. If you're not familiar with them and you want to do some audio programming, you'll probably need to like revisit that and learn a
Yeah.
little bit about it. But I think the key point, the point that I come across most frequently is this idea of like these kind of like key ratios in the sine function, right? When is the sine function 0? When is the sine function 1? When is the sine function -1? And those are kind of like the key angles that you need to know.
Nice. There was a time when I knew all those pretty intimately.
If you don't practice, it just like
Yeah.
it's just gone. All right. So yeah, early in an earlier video, you were talking about the Fourier transform. Let's talk about the Fourier transform. This is a really important one that you'll come across a lot in audio programming. Usually, it's in the form of the fast Fourier transform, which is like a specific implementation of the Fourier transform. But the basic idea here is that we're taking a sound from the time domain. So, earlier we looked at a waveform in Audacity, right? That's in the time domain. We're seeing it. The x-axis is time. Um, the Fourier transform takes something like that and converts it to the frequency domain, meaning the output is it's a series of bins where each bin is a specific frequency range, and it tells you the amount of each frequency that is in that range. And those frequency
Yeah.
ranges can be represented as a sine wave.
Yeah, it's coming back to me.
It's it's kind of wild, and the really wild thing about it is that it's totally lossless. Like you can convert
Yep.
from time domain to frequency domain and back to time domain without any loss of information.
I really just remember in like our signals class, like we had like a chart, like a cheat sheet for the Fourier transforms, and so like we would like there was one for like each of the main trig functions like sine and cosine and tangent. They all had like a transformation they do in the other domain,
Mm.
and that's about all I remember.
So in when we're talking about audio stuff, usually what we're talking about is much more complex than like a single sine wave. You know what I mean?
Yeah.
Like any given audio signal in the real world consists of many frequencies. And so, yeah, what the Fourier transform results in is like this much of this frequency and this much of this frequency. This is
Mm.
um, so yeah, it's kind of interesting. Like what you're talking about, it's like a pure sine wave would have a specific signature in the Fourier transform, right?
Yeah.
It would look like this. And in the real world, an audio signal is going to have like a little bit of this, a little bit of that, but a lot of this. Like there's usually going to be a primary or a couple
Yeah.
primary frequencies.
So yeah, so you had your cheat sheet, which would tell you like those transformations, but then the actual problem would be like multiple things, and there was rules to how they would transform when used together.
Mm.
It was like
Mm-hmm.
a whole thing, kind of like when you take derivatives and integrals, right? It's like there's a way to do it, that there's a way that they move around. It's like a similar thing to that.
Hmm. Okay.
I can't talk much more about it. That's really all I remember. It was a very tough class for me.
But like, um, are you talking about? So when you would have a problem like that, are there specific? Would they give you a series of sine waves and be like calculate the transformation? You have to calculate like the. Are we talking about like waveform interference kind of things
it
here?
would it would be like I mean the problems would be like sine of something minus the arc tangent of this divided by the derivative of this or whatever the fuck.
What?
And then you had to like find it, and there was a way to how it worked. Um, um, yeah, I wish I remembered better. I'm trying to look up cheat sheets and stuff, and I'm like, I don't know, was this it? Okay. Oh yeah, yeah. Okay, this was part of it too. Like translations, time delay. So they. I feel like if I start trying to like try to figure this out in the video, I'm just gonna look stupid. But I'm gonna send you this image, and you can tell me what you think. How do I? There we go. There's the chat. I think I sent you the whole. Yeah. Okay, that's good.
I think I can pull that up. Let me see. Oh yeah. What the hell? Yeah, so I'm gonna be honest, I just let the computer do that.
Yeah.
I mean, any audio framework is gonna have like FFT function built in, right?
Yeah. I don't really, but I remember like some of the problems would be word problems where it's like there's a time delay of this much, so that means the signal has minus t, and then the so ft in f is the is the time domain, I guess. I remember the f versus omega thing. I don't remember what they mean.
Yeah, I
But so
don't
like
know.
in one of them, oh no, f is frequency, and then omega is phase, I think. I don't know, dude.
Oh, yeah, yeah.
Whatever.
Well, I think in general you won't need to get that deep into it. Basically,
Yeah.
the the important part for the important part for audio programming is that this function takes in a chunk of audio, an audio signal in the time domain, and it outputs something in the frequency domain, which is like a representation of how much each frequency is represented. And there are a discrete number of bins in the frequency output, and the output kind of tells you like there's this much of this frequency, this much of this frequency. And so like if you see something like this, that's what they're doing there. They're taking an audio signal and they are analyzing how much of each frequency is in each bin, and then basically that's the output, right?
So what is the x and y axis of this chart right here?
The x-axis would be the frequency, and the
Mm-hmm.
y-axis would be the volume or the
The volume.
amplitude within that frequency.
Okay.
And so this is just the output from like I think it's like from VLC or something, you know.
Yeah.
So it's not mathematical or anything. It's just trying to represent something pretty. But
Yeah.
it's but yeah, it's basically base frequencies on the left side, higher frequencies on the right side, and then how much those frequencies are like being represented.
Yep.
There's a lot to get into there. If you're interested in that, you'll need to read up on like their windowing functions. Obviously, if you take the FFT of like an entire 4-minute song or something, there, you know, a lot of frequencies are going to be represented in a 4-minute song, right?
Mm-hmm.
You need to take them kind of chunks at a time, and there are windowing functions to help you with that. Um,
Okay.
that's its own kind of thing, but it's just worth being. I think for starters, it's worth being aware that there is a thing called the FFT, and that the FFT converts time domain to frequency domain, and that the output of the FFT is these bins of frequency, and it tells you how much of each bin is represented.
Yep. Cool.
All right. Next, we're going to talk more about samples and about some real-time constraints.
Oh yeah.
See you next time.
1x Developer Podcast.
Hey everybody, this is Colin. First and foremost, I want to thank you all for listening to this episode of the 1x Developer Podcast, and let you know that if you have any questions, comments, or if you just want to tell us about your day, you can reach us at X, formerly known as Twitter, at 1x Developer Podcast. We're also on YouTube at 1x Developer Podcast. You can email us if you're weird at 1xdeveloperpodcast at protonmail.com. And lastly, don't forget to follow, subscribe, all that stuff, so you don't miss any further episodes of the 1x Developer Podcast. Thanks so much. See you next time.